Okay, let's continue with our introduction to flatness in several types of systems. The systems we're reviewing now is linear time invariant systems, and the first representation we studied was the transfer matrix representation. And in there, many things mimic the single input, single output with the generalization to matrices of left and right coprime factorizations. But the concept of flatness is still the same. It's an endogenous, in that case, set of variables, which has to have the same cardinality as the control input set. So if there are m control inputs, there should be m flat outputs. And they are components of that vector of flat outputs do not satisfy differential equations by themselves. In the algebraic language, one says that set of variables is independent. Independent in algebra means they're not related to anything else. Being independent in that context means they're endogenous. You don't need anything from the outside of the system to define it. So now we have to come to the state space representation of multivariable linear time invariant systems. That's a class of systems where the flatness also extends quite directly, but one in which several features start to appear. Like there might be many flat outputs. What is the process by which one can compute the different flat outputs, and so on? Is this scheme of finding the flat output unique or not? So we will concentrate on linear time invariant systems where you have m control inputs, and the input to state relation is dictated by this set of linear differential equations. And we will assume that the matrix is full rank. This is just a common assumption. So the rank of B is just M. B is a matrix which has n rows and m columns. So this is a fundamental assumption, just to say that there is no superfluous control inputs acting on the system. Every input sort of influences some part of the state space, and this is achieved by this elementary assumption. And then the issue of controllability, which was proven in the previous lectures to be equivalent to flatness in the linear case, and even for the transfer matrix representation, here we encounter the same possibility again. The controllability of this linear time invariant multi-input system is completely equivalent to the controllability of the system. So flatness and controllability remain to be equivalent, remain to be the same thing in the context of linear systems. So the Kalman controllability matrix is the usual way to verify if a system is controllable or not. The only variance with respect to this single input case is that you now have a rectangular matrix for the Kalman controllability matrix. You have n rows and m times n columns. So the matrix, the Kalman controllability matrix, belongs to this space. And we call it K sub C in this case. So it's a rectangular matrix. There is much more columns than rows. Therefore, we have to find that the smallest set of linearly independent columns, and in the case of flatness, we should be careful about how to proceed to find a matrix that describes the controllability and at the same time allows us to compute the flat outputs. And in this case, we will have m of those flat outputs. So the system is said to be controllable if this matrix is full rank n. I mean, the column rank cannot exceed n, and we have much more columns than rows. So this is the controllability condition. The rank of C should be n, and how to choose those n independent columns? Well, there are many variants to do that. Then we were going to stick to one, which is the most practical, let's say, and at the same time it also gives us the possibility of establishing what is called the controllability indices, the Kronecker controllability indices, and these Kronecker controllability indices are going to give us the possibility of having a formula for computing the flat outputs, and that formula is important. So the ways to establish a meaningful set of columns in the Kalman controllability matrix which span the whole n-dimensional space ascribed to the state of the system, we start by assuming that the rank of B is m, and therefore we will first write all the columns in the matrix B as one candidate as candidates for the rows that will remain in our study of the Kalman matrix. All we have to do now is to fill up this matrix so that all the columns are linearly independent, and each one of these blocks represented by the first input channel, the second input channel, and the nth input channel are appropriately filled with powers of A multiplying B until we find some kind of linear dependence, and then we'll stop the process and continue with some other channel. But many things can happen in between, and the things that can happen is that maybe the system is controllable from a single channel or from two channels, and therefore we will fill up this matrix very quickly, and probably other inputs will not have the chance to appear, and that's part of the consequences of the multivariable nature of this system, of this linear system. So one of the things we can do is start filling these rows by things like AB1, AB2, ABM. Of course, the B1, B2, BM are linearly independent. When we put this one, we have to make sure that it's not dependent on any of the existing columns that are already in the matrix. Because if that is the case, then we should stop filling up this block of matrices and continue with other. But let's assume that we can do that sequentially, and that each time we put a power of A multiplied by a corresponding B, we still get some linearly independent vectors or column vectors that still don't comprise the entire n by n matrix. So this is a sequential procedure that can be easily implemented, but you have to be careful and check at every time, because it might happen, I repeat, that one of the channels is more powerful than the others in the sense that by itself can control the whole system, and that will happen in an example that we will present. So we start filling each one of these blocks by multiplying powers of A, successive powers of A with the corresponding B, and at each step checking that the newly obtained column vector is totally independent of those we already have in the collection. So the assumption is that for the first block influenced by the first input channel, you can put powers of A in combination with B1 that reach the power gamma 1, let's say, -1. And if you compute the next one, it will become linearly dependent of some of the vectors we already have in that matrix. So we proceed to compute the other powers of A, multiplied now by B2, until we reach a new power, gamma 2 -1, say, beyond which the newly obtained column vector becomes linearly independent of those we already have. That might happen, and therefore we can fill up the whole matrix with several powers of A influencing each of the column matrix of B until we complete an n by n matrix. That's the process. There are other processes, different processes, by which you first exhaust whatever you can achieve with B1. And then when you compare all those column vectors with B2 and Bm, you find out that they start becoming linearly dependent, and then you stop and continue with B2 and so on. But at each step you have to verify that all the vectors you have here, all the column vectors you end up with, are all of them linearly independent, and they are n in number. So you have gamma 1 vectors in the first block, gamma 2 vectors in the second block, gamma n vectors in the n block, in the nth block. So we will call those powers, gamma 1, gamma 2, gamma m, the controllability indices. And when you add them up, you should obtain the order of the system. And the order of the system is n. So that's a preferred procedure, and we will show through an example that several things might happen. That those indices are not uniquely determined from the way we have indicated how to fill up the controllability matrix. There might be other ways to fill it up, and they produce different controllability indices. Let's suppose we have the equations, the linearized equations representing the orbiting satellite that we had as a nonlinear model in one of the previous lectures. So we have the matrix A and the matrix B well identified in our state space model, which is fourth dimensional. And so we have two column vectors which evidently are linearly independent. So we can put those vectors right away, like B1 and B2. One way to fill up the controllability matrix is exactly as it is written in the definition. This would be the way to put this block B, AB, A square B, all the way up to AN minus 1B. This is one way to fill up the controllability matrix. So in this example, we're putting B first, the two column vectors of B. Then the next two represent the product A times B. The other next two represent the product of A times the previous one, that's A squared times B, and so on, all the way up to A cubed times B. The system being fourth order, we have to reach the power A cubed, the power 3 of A multiplied by B. So A cubed B would be the last set of two columns in this matrix. Now the problem is to choose from them those which correspond to this distribution of the columns of A and B in the Kalman controllability matrix, so that we get a 4x4 matrix. So one way to do it would be to choose B1, and then we see that AB and B2 let us write it here to indicate how we did it. So one way would be to take the first column of B and the second column of B, which would be 0, 0, 0, 1. So we multiply A times the first column of B, we get B1 and AB1. So B1 is this, AB1 is this, so the second column would be 100 minus 2W. That's AB1. And now we have B2 here. All of them are linearly independent, evidently. So they stand out. We only need one more. We take B2 and AB2. If we take AB2, this would be B, AB1, AB2 would be 0, 2W, 1, 0. So all of them are linearly independent, evidently, and therefore this is a full rank controllability matrix. Okay, so from here the power of A reach gamma 1 minus 1 is 1, so gamma 1 is 2, and gamma 2 minus 1 is 1, so gamma 2 is 2. 2 and 2 is 4. 4 is the dimension of the system. This is a nice controllability matrix, and the Kronecker controllability indices are gamma 1 and gamma 2 equals 2 and 2. Okay, that's one way, but we could proceed in a different way. Once we have all the column vectors representing the Kalman controllability matrix, we could have done something like this. We stick to B1. B1 is 0, 1, 0. Then we put AB1. The second one we put is this one, and that's linearly independent of the first one. And then we put A squared B1, and we still get a linearly independent vector from the previous collection. So we run into the possibility of not having B2 being represented here. So we see that B2 is already linearly independent of AB1 and A squared B1, and therefore we put B2 here. So in this case, B1 goes all the way to A2 B1, and in the second block we don't have any power of A. So the controllability indices for this matrix would be 3 and 1. That's also valid because the obtained matrix is also full rank. So in the second case, we get gamma equals 3, gamma 2 equals 1. The addition of those two indices is still 4. Therefore, we're in good shape. This is also a good representative of the Kalman controllability matrix, which is full rank. It shows that the system is controllable from U1 and U2. And it's a full rank matrix, and therefore the controllability indices are well defined, and they have these values. This is a different set of values from the previous one. And in this particular case, we even have the extreme situation in which if we only take, let's say, B2 now, which is this column matrix, and start putting powers of A, multiplying B2, all the 4 resulting columns with powers of A ranging from 0 to 3, they will all be linearly independent. So in that extreme case, the controllability indices are such that the first column B1 doesn't even appear, so the controllability index is 0 for the first input, and the controllability index is 4, complete order of the system for gamma 2. So we have 4 different situations, and 3 different situations, and that gives us different choices for the controllability indices.
So the last case, did you try to use the B1 at all? Or just
no, we just noticed that this set was linearly independent, so it qualifies as...
It can be controlled by
yeah.
U2.
Yeah.
No.
This system can be controlled by a single input channel.
Right. So does U1 provide anything at all? I mean, when you say R1,
yeah, A1 wouldn't be doing anything.
So it doesn't do anything?
Doesn't do anything.
Why do we have U1 in there anyway? I mean,
well, this is an actual example of real life. Satellites only need tangential control to go up in the orbit or to accelerate, to go up to the orbit or to down, or to get down from the orbit it is. Only tangential acceleration is needed. But if you have thruster for the tangential and the radial, then you are in any of these cases. You can control the system by this. But it turns out that from a single channel, you can control the radial position and the orbital angle.
So the second case, does it tell you that the U1 is more dominant than U2?
Yeah, U1 has more influence over a larger dimensional subspace of the state space.
So
Yeah.
could it be a third case where R1 equals 4, R2 also equals 4?
I don't know, I have to check this.
Could be, right? It's possible.
If R1 were what?
So it could be possible that the system is completely controllable either using U1 or U2.
Yeah, which I don't know if that's the case here, but you have B1, A B1, A square B1, those are linearly independent, and then you would have this one, yeah, this one is a linear combination of this, so it doesn't work. Here it's not.
But it's possible.
Yeah, it might be like here. It's possible that this thing was controllable from a single channel, but in this particular example, that cannot be, because when you control only the radial position, then you cannot control the other one. So you cannot control both things with the first control input. So this is one of the things that is transparent from this example. There are some multivariable linear systems in which the controllability indices, passing all the possibilities, can give you complete controllability from a single channel. And well, that means that in some instances you don't need the two controls. You will be perfectly fine in regulating your system to any other point or any other subspace of the system by means of a single controller.
And here has an interesting example. He put two motors in the motion system, both from. So I think the system can be controlled from both motors.
Okay.
But one motor is for the coarse, one motor for the fine. So I think that might be helpful for you to reformulate the problem a bit more.
I think maybe it's possible to use the fine the motor.
Yeah.
Yeah, we can discuss the detail later, but
yeah, that would be interesting to have an example in which that property is evident, which tells you can control this system from a single input channel. That would be advantageous in many situations. So how to find the flat outputs? Because remember, the flat output was very much related to the controllability matrix in the single input, single output case. And in the multiple input, multiple output case, or MIMO case, we seem to have different choices for the Kalman controllability matrix, in which the influence of each particular control shows up differently regarding the dimension of the subspace that it can actually influence. And so let's do the dual approach as we did in the single input, single output case. Remember, the observability matrix was also very much related to the possibilities of parameterizing every state variable by means of the flat output. So suppose, as we did in the CISO case, that the flat outputs are endogenous functions. That means they don't satisfy differential equations by themselves, and that because it's linear, we can assume safely that the set of flat outputs, this is an m-dimensional vector, that the set of flat outputs is related only to the state and not to the input. That can always be done, to have the flat output be related only to the state. Remember that in single input, single output, when we computed the flat output using the Besut identity, the flat output came out to be a linear combination of time derivatives of the input and the output. We can eliminate the presence of the input in general manner And also in the multivariable case, we can do that. So the controllability matrix lambda here, the observability matrix lambda here, is an m row, n column matrix. There's a mistake here, it should be lambda sub m. So, so that's an m times n matrix, and it should be full rank m, because we have m outputs. So let us form the, let us form the n times m plus 1 column vector with the successive time derivatives of the components of y. We put the whole vector y here, the whole vector of first order time derivatives, the whole vector of second order time derivatives, and supposedly we could stop at the n minus 1 vector. So we have a bunch of extra derivatives which make this a very long vector, n times m times one column, but n times m rows. And what we want is to extract from there, in terms of the A and B matrix, the influence of this observability matrix. So we can explicitly write down y in terms of lambda x, and there is no further relation with anybody, not even the control input. But y dot, which is lambda times x dot, will have lambda multiplied by a, and then x, and then the influence of the control starts appearing. So as you take more and more derivative of this m-dimensional vector y, you will start filling up in a very redundant manner. This matrix will be now the matrix ranging from the power 0 of A all the way to the power n minus 1 of A. So we have a large matrix there, and which has much more rows than columns. It only has n columns and n times m rows. And the influence of the input in the derivative of the higher order derivative of the output passing through the state will start involving derivatives of u, all the way up to possibly n minus 2. Remember that u will always be present in one of these simple manipulations. U will be present with one less derivative than what you have for the output in this case, which is a direct linear function of the state, and it doesn't include the inputs. So we have the complete map in which the derivatives of that n-dimensional vector y is related to the n-dimensional vector x, and to this arrangement of successive time derivatives of the vector u, which is also m-dimensional, from derivatives of order 0 all the way up to derivatives of order n minus 2. And of course we would like to choose only n linearly independent rows in this observability matrix, which is a very tall matrix in the sense of having much more rows and columns. And we can proceed in the same way as we did for the controllability. We can pick up, let's say, the first row of lambda, the second row of lambda, the nth row of lambda, and then filling up by powers of a on the right, multiplying those row vectors lambda 1 by a squared, a cubed, and checking that the ones we have already in the matrix, which were at the beginning all the rows of lambda, checking that none of those powers start becoming linearly dependent on the rest of the written row columns, row vectors. So this is a similar procedure to the one we use to fill up the controllability matrix by choosing first the row columns of the lambda matrix, and finding that they're linearly independent, we leave them there, and we start filling up with powers of a on the right of these row vectors. Until we do that for each row vector, we can fill up with different powers of a. here we say that this power of A is of the order rho 1 minus 1. For the second row vector lambda 2, we can reach 2 minus 1. And that for the last vector lambda m, the last row vector lambda m in the column, in the matrix lambda, we reach a rho m minus 1. If that is the case, and the sum of those rows is equal to n, then we will end up with an n times n matrix representing linearly independent rows of the observability matrix as defined originally by Kalman. The observability matrix, of course, has a lot of redundant vectors, because we would have the entire matrix C here, CA, and so on, all the way to CAN minus 1. But remember, C is a matrix of m rows and n columns, and A is a matrix of n columns and n rows. So the product of C, CA, CAN n minus 1 will have n columns, but it will have n times m rows. So it's a taller matrix, it's a rectangular matrix which is of the tall type. It has much more rows and columns. So we have to pick up from there those which are linearly independent and that somehow involve all the row columns of C, which is supposed also to be full rank. C, the rank of C is assumed to be m. And by doing that, we obtain a different set of Kronecker parameters. They are called the Kronecker observability indices. And the nice thing would be to relate them to the Kronecker controllability indices. So if we do things in the right manner, we can choose the row vectors to be orthogonal to the set of independent vectors in the corresponding block of the Kronecker decomposition of the Kalman controllability matrix. We decompose this in blocks of the form bi, abi, all the way to a gamma I minus 2 bi. And the next one would be a gamma I minus 1 bi. So we could choose these observability row vectors to be orthogonal to the gamma 1 minus 1 first controllability column vectors, and align the last one with the next power of a to the gamma I minus 1 bi, or a to the gamma I minus 1 bi. So what we do is we will be able to choose these observability, the rows in the observability matrix in such a way that block by block, because we have been able to define blocks for the observability and blocks for the controllability, all these blocks have the following property. The first block of matrix of rows, all of them are orthogonal to the corresponding controllability blocks. But the last one will be aligned with the last one of the controllability block, corresponding to the first input, first output. So we can do that because we have enough freedom, and we make this clear. Lambda 1 has to be orthogonal to all these column vectors in the Kronecker module corresponding to the ith input. But it will be aligned with the last possible power of A multiplying bi. And of course, still being orthogonal to the rest of the elements in the Kalman controllability matrix. When we do that, we obtain a very nice property. All the columns of the controllability matrix and all the columns of the observability matrix will be orthogonal, except with those vectors which indicate the index of the controllability, the Kronecker controllability subspace, and for that we will obtain just a simple alignment, a constant, and the rest of the products of these observability row vector with the rest of the columns of the controllability matrix will be 0, will be orthogonal. So this is like defining a new basis for the lambdas so as to make the Kronecker indices of the observability matrix match those of the controllability matrix. This is the crucial thing, something that we didn't have in single input, single output systems, but because of that, we get immediately the interesting result. The flat outputs will be related to the fact that the flat outputs, each one of them is independent. The collection of flat outputs span the whole state space when combined with sufficient powers of A, and they will also correspond to observable outputs. So the flat outputs will enjoy this kind of controllability and observability property in the cleanest possible way, in the way in which the controllability indices for the Kalman matrix will coincide in the controllability case with those of the Kronecker indices in the observability matrix. When those things match and you put this orthogonality conditions on the sub-blocks representing each one of the Kronecker blocks, except for the last one where you let the vector lambda I be non-orthogonal but align with the last one of the last column vector of the controllability block corresponding to that Kronecker index, you will have a realization of the flat output which enjoys both the property of being the best set to control the system and also an observable set in some sense. So the net result is that the flat outputs are such that the Kronecker observability indices coincide with the Kronecker controllability indices for the corresponding input. So this will create an input to flat output relationship which is very well geared towards solving one of the most significant problems in multi-input, multi-output system, which is the decouplability. Somehow we want each control to be in charge of a set of outputs, and the interference can be eliminated from the action of the controls trying to control its individual subspace of the state space. So in essence, what we are after is a formula for being able to compute the flat outputs, which also generalizes the formula that we found in the single input, single output case. In the single input, single output case, we only had observability and controllability of a single variable, and we could obtain the flat output by means of a state coordinate transformation involving the inverse of the controllability matrix, and that allowed us to say that the corresponding flat output was the last row of the inverse of the controllability matrix. Here the situation is more general because we have geared things up in the input to state and state to output structure so that each input will be involved only with a subset of the set of outputs whose range has the dimension coincident with the dimension of the highest controllable subspace from that particular input, where you respect the Kalman controllability matrix order in a definite and clear way. So when we do that, we obtain that the product of the lambda controllability matrix multiplied by the Kalman matrix that we have ordained and that we have built up with those independent columns is that you will have always orthogonality of the rows of lambda with all the columns of the Kalman matrix, except at those points where the corresponding power of the Kronecker index for the controllability matrix coincide with the Kronecker index of the observability matrix. So you will have zeros, and let's say a constant that can always be put as a 1, in each row vector of this product of lambda times the observability matrix times the Kalman controllability matrix, you will obtain zeros and ones exactly located at the Kronecker. The Kronecker is an integer, so at a distance from the left column that is equal to the number of columns represented by the Kronecker index. So this one appears at the gamma 1 location in the first row. In the second row, you will have the Kronecker index corresponding to gamma 1 plus gamma 2. You will have a 1 there and zeros everywhere else. And in the last row, you will have the one appearing at the gamma 1 plus gamma 2 plus gamma 3, etc., up to gamma m. In the last one, you will have a 1 right there and zeros everywhere. So this means that the products of the rows of this observability matrix times the columns of the controllability matrix will all be orthogonal except at those powers of A which reflect the Kronecker controllability index. So this is like a transformation that can be used for the state space, and therefore we form the controllability, the observability matrix as the product of these column vectors which are regulated by the Kronecker index, like gamma 1 here, zeros everywhere, gamma 1 plus gamma 2, 1 and zeros everywhere, gamma 1 plus gamma 2 plus gamma m, 1 here and zeros everywhere. So these vectors are called O1, O2, O3 and so on, all the way up to OM. So the observability matrix is this set of very simple rows of zeros and ones multiplied by the inverse of the controllability matrix. So the observability matrix is the inverse of this matrix multiplied by this matrix, which reflects all the Kronecker controllability indices, matched with the Kronecker observability indices. So this gives us a way, by using these matrices as part of the state coordinate transformation, that the m-flat outputs are given by multiples of the linear combinations of these state vector components obtained with the m rows of the inverse of the controllability matrix, whose positions coincide with the values of the ordered sums of the Kronecker controllability indices. This is precisely the matrix that allows you to compute. Remember, this lambda is the relation between the inputs, the outputs and the state. So by using this relation written in this form, we have a formula with this set of zeros and ones that generalizes the single input, single output case, uses the inverse of the established controllability matrix in which the Kronecker indices are clearly laid out, and we will just simply take the product of this matrix of zeros and ones times the inverse of the controllability matrix multiplied by the state. Those will give you the m-flat outputs. Each one of these columns will pick up the corresponding relations with the state through the inverse of the controllability matrix to produce the flat output. So you will have only m flat outputs. So the rule is precisely a generalization of the case in the single input, single output case, in which you have only one input and one output. And this was the case for the controllability index. The controllability index in that case was n, because the system was assumed to be controllable, and the flat output is observable. Therefore, the relation of the controllability matrix and the observability matrix would produce something like that if we choose the rows of the observability matrix to be orthogonal to those of the controllability matrix, except the last one. And in the last one, we'll have an alpha here, which gives you the proportionality. and the freedom to choose your flat output up to a constant factor. So this is the recipe for multi-input, multi-output system. It's more general. It's a little bit more complicated, but once you decide what set of controllability indices you're going to stick to in the possibilities that the Kalman matrix gives you as indices reflecting the influence of each particular input into the state space and the span of each particular input into the state space subspaces that it can influence directly, all that remains now is the problem that they will be interacting. Somehow they will be interacting through the control structure, but at least from a point of view of practicality, you will have the flat outputs as the set of vectors that completely differentially parameterize the whole system, all of the states and all of the inputs, and by ascribing trajectories to those flat outputs, you have trajectories for the states and the inputs. And that's an analysis tool that is very nice to have around. And also those are significant outputs because they span a certain subspace of the state space, which complements very well with the rest of them without interfering in the observability of those particular outputs. And therefore, everything is sort of prepared for decoupling the system in a closed loop fashion. That's probably the.
So the transfer function matrix from the input to the applied output, would that be diagonal?
No.
You said you decoupled it.
It's geared to be decouplable, but it doesn't mean it will come out to be decoupled. Oh. But it's very clear that you will be able to do it by feedback in this particular case. No, this gives you a structure in which you still have interaction of the control input variables mendling into the subspace of each of the others, but everything will be so clearly presented that you will be able to say, how am I going to decouple this? And particular cases involve that the matrix relating all these outputs to the inputs will be invertible. You remember, we're in the presence of a square system. We have as many flat outputs, M, as inputs. So in the input to flat output relation, you will have possibly a matrix which is invertible. Okay.
What about the zeros?
There won't be any zeros.
So that transfer matrix have any zeros, transmission zeros.
Yeah, but for the now we have to decide: are we sticking to the originally given outputs, or are we talking about the flat outputs? The flat outputs don't have any zero dynamics. All of them completely cover the state space, and they don't have any zero dynamics. This is the same as in the single input, single output case.
I'm talking about the transfer matrix and the transmission zeros defined for that transfer function matrix. Would that there will be no transmission zeros in that transfer function matrix? Remember how we defined the zeros of a system? Exactly. So that's the definition of your zero.
Yeah, and remember that one of the conditions we were imposing was the special character of that matrix multiplying the input. It had to be a matrix with a determinant that was constant. So the minor corresponding to that matrix has no zeros or poles. So in this particular instance, the multi-input, multi-output case recovers some of the nice features of the single input, single output case. And so this observability matrix, when you take the inverse, you find the relation between the state and all the outputs, and you will see then that the vector y, these are the flat outputs, the vector y differentially parameterizes all the states. So every state can be written as a linear combination of components of the flat output vector and a finite number of time derivatives. So at the end, the state-dependent input coordinate transformation, the flat outputs y, differentially parameterizes states and inputs. And the input to flat output relationship would be of this sort. Naturally, you can have this after some input coordinate transformation, you might have this complete decoupleability, and U1 is differentially parameterized by gamma y1 and a finite number of its time derivatives, and so on. So you have chains of integrations for each one of the inputs associated with the flat output and a finite number of time derivatives of each flat output. So the structure is very nice, is very amenable to.
Are we missing something here? U1 equals Y1 to the R1? Are we missing?
Yeah, we might have some relation, but after a coordinate transformation of the U1s, we have this clean Kronecker, this clean Brunowski forms. This is a chain. So by simple state feedback and redefinition of the inputs.
It might be a V1, right? That's you use a pseudo. That's not the original U1, is it?
Yeah, it's not the original U1. Yeah. That would be correct. So as I say here, after a state-dependent input coordinate transformation, you will have that. Yeah, that wouldn't be the original. But you have the decoupleability very nicely presented in terms of the flat outputs, and that's what we're after.
So that transfer matrix corresponding to that equation not only diagonal, it's a cascade integral.
Yeah, each flat output will be a chain of will be present in a chain of integrations corresponding to one transform input.
Right.
So you have the couplability.
That's exactly. That's
yeah, but
in a Brunowski form.
Yeah, in a Brunowski form. But remember, this is after a state input dependent coordinate transformation, not before.
分块，对，它不光分块了，它 Brunowski form， 它变成那个分音序。
Let's see how this applies to, for instance, the satellite system in which we had this Kalman controllability matrix, and we choose the case in which we have gamma 1 equals 2 and gamma 2 equals 2. So for that particular case, because we could also have gamma 1 equals 3, gamma 2 equals 1, and so on, and in this case, the Kalman controllability matrix reduces to this 4x4 matrix, which is invertible. And in that case, the two controllability indices add up to the order of the system, which is n, in this case 4. So the inverse of the matrix C, the controllability matrix, determines through this particular matrix in which you have the first row has 2, the controllability index is 2, so we'll have 0 and a 1 in that row. The second Kronecker index is 2, so you have 2 plus 2 is 4, so you'll have zeros and 1 in the fourth location of this matrix. So this multiplied by the inverse of the controllability matrix will give you the flat outputs. And with those flat outputs, then you can proceed to find the differential parameterization in terms of, let's call x1 f1 and x3 f2. The differential parameterization is immediate. You will have, you have that x1 is just the first flat output, x2 is the derivative of the first flat output, so that's f1 dot, and u1 can be computed in terms of f1 and f2. You see, you do have some interaction of the higher of the derivatives of each flat output intervening in the parameterization of each control. x3 will be taken to be f2 and x4 f2 dot, so u2 can be put as as this sum of derivatives of f2 and f1. So with that in mind, you know that you have this input to flat output relation. And what is significant here is that we should take care of the maximum order of the derivative of each flat output appearing in each expression. So f1 here appears as a second order derivative. That's the dominant dynamics to be controlled by u1. The rest is the interaction between the two subspaces, and it involves f1, which is not bad, but it involves f2 dot. And the parameterization of f2 is given out in terms of the second order derivative of f2 as the Kronecker controllability index dictates, but you also have the influence of f1 dot in the conformation of u2. But here is easy to design a state coordinate transformation. Remember, now my state is f1, f1 dot, f2, f2 dot. So the phase variables associated to the two flat outputs is a natural state space. So with an input, a state-dependent input coordinate transformation, I can redefine this u to eliminate the influence of the second block into the first by redefining my control so that this terms is eliminated from the left when it appears on the right. And the same I can do here for u2, redefine u2 so that the influence of f1 is eliminated. So the new u1 will only depend on f1 and times the derivative of f1, and u2 will depend on f2 and times derivatives of f2. So you can decouple very easily the problem, and that's also a nice feature in multivariable systems of the flat outputs. They naturally give you a way to decouple the sub-dynamics that integrate the whole thing in an ordered fashion. So it's if you want to live with that influence, nobody will be forcing you not to eliminate those, but remember, this is the actual relation of the actual inputs with the flat outputs, and you have some interaction, which is natural in a multivariable system. But you can decouple that interaction by feedback or by redefinition of the control inputs. That's the point. So in that example for the satellite system, we took that definition of the flat outputs. It's just the radial position and the angular position, and the parameterization will show you everything you need to know about the internal features of the system. Okay. So you can redefine your control inputs by means of a state-dependent input coordinate transformation. When you do this for u1 and u2, you put an auxiliary input v1 here and auxiliary input v2 here. You eliminate the influence of the first flat output on the second parameterization, on the parameterization of u2 by the second flat output, and you will obtain two chains of integrations which are independent in the auxiliary variables for the input v1 and v2. So you have two chains of second order integrators. At the heart of this linearized system that is describing how a satellite behaves in a circular orbit around the Earth, how to control it. This would be one of the ways to carry out their analysis and their control. If on the other hand we would have chosen the controllability indices to be 3 and 1, so this would be the Kalman controllability matrix. It would have 3 columns associated with the first input channel, and it will have only 1 column associated with the second input channel, and still the controllability matrix would be full rank matrix, so that the Kronecker indices would be 3 and 1. So now the flat outputs are obtained by the inverse of that particular controllability matrix that you have chosen, multiplied by the states, and the matrix that you should use to fish out those controllability matrix would be related to these indices. So the first one is 3, you put 0, 0, 1, the unit vector gamma 2 and zeros, but the process is finished in that case. All right? So, so you take the controllability matrix that gave you these Kronecker indices, you invert that, multiply by the state, and now you have a set of 2 new flat outputs, which are a little bit more complicated to use than the first one. So one of the flat outputs is proportional to x3, and the other flat output is proportional to the sum of the radial position and the angular velocity. And so that's kind of mixing the physics and the mathematics of the problem. But that's the way it is. You can obtain equally, you can obtain the differential parameterization of all the state variables x1, x2, x3, x4. Before we have flat outputs which were coincident with x1 and x3, but now we have different flat outputs which are a combination of x1 and x4, and the other one is proportional to, I believe, x1, x3. And now you have a different parameterization, and of course the control input, the control input U1 and the control input U2 will have parameterizations that correspond to the Kronecker indices, 3 for the first control and 1 for the second control. So this, you see, the influence of F1 is very important in U2 because it appears with third derivative and second derivative, and the subspace that is being controlled by U2, represented by the flat output F2 and its time and its span with the derivatives of F2, the phase variables associated to F2, it only takes F2 dot. So in essence, the second system is a first order system, and all these higher order derivatives is the influence of the first on the second. The second also influences the first by a first order derivative and a second order derivative. But here you can redefine this as an auxiliary output and this as another auxiliary output, and hide all this dependence on the interaction, hide it behind a set of auxiliary inputs in which the integration structure of the system inputs towards the flat outputs is clearly exposed as a chain of Brunowski form of order 3 and a chain of Brunowski form of order 1. So that gives you a nice internal structure of the system in which you can control. Now the problem is designing a control for that, and if you insist in this parameterization, you know that all the extra terms will represent disturbances, internal disturbances that you might care to eliminate or to maintain them alive, and then cancel them appropriately by estimating them. So the problem again is in the multivariable case. This is very well geared towards applying ADRC control. It's immediate that the parameterization gives you the relation that is important. What effort should be placed in controlling the first flat output from the first input, and what effort should be placed for controlling the second flat output from the second flat output from the second input, in spite of all the interactions. This is the interaction of the first subsystem towards the second. The interaction of the second towards the first is represented by these two terms. So you have vivid, explicit dependencies among the subsystems, and you can also have the internal structure, the heart of the system, laid out for you as two subsystems of third order and first order respectively. And that simplifies the control issues enormously. And I'll show you a very simple example of physical nature with the PVTOL airplane. This is the vertical takeoff and landing model of the airplane.
Make it bigger.
Pardon?
And make it bigger.
Yeah, yeah, because you can. Yeah, that's better. That's much better. Thank you. So this is a simplified model of the aircraft. It's a nonlinear model, very well known. It's a non-minimum phase system. The natural outputs, which is the natural outputs of this system, which are the horizontal coordinate of the center of gravity and the vertical coordinate of the center of gravity. Those two outputs are non-minimum phase outputs. You regulate them directly. The zero dynamics will be associated to this angle, and it will start rotating at the slightest perturbation. So this is a nice multivariable example. Nevertheless, the nonlinear model is flat. That model is flat, and it has a flat output, which is combinations of the x and the c's. But the issue is to linearize the system around an equilibrium. You linearize the system by letting theta to be 0, so it's in horizontal plane, horizontal flight coming out of the blackboard, and gravity is normalized to this force associated to the height, and it doesn't have any influence on the horizontal dynamics. This is the horizontal dynamics, this is vertical dynamics, which are somehow coupled for the control inputs. The control inputs are the lifting force, the lifting force. These two motors exercise some force, and the vertical components will be related to the lift, U1, and the difference of those two forces create a torque on the axis of the airplane. So you have two inputs, vertical lift, which is a force U1, and U2 is a momentum, is a torque. So you have you can linearize the system around the operating point, in which you have a nominal horizontal and vertical position, which is in equilibrium, and the angle is 0, and the forces, the force U1, the lift is counteracting the gravity, and you don't have any torque applied on the system. So the system is in equilibrium. Now the problem is that you want to go somewhere else in a controlled fashion. The system being nonlinear, the linear model is supposed to be good only for small deviations, while flatness allows you to take the airplane really far away, and it will excite the nonlinearities. And in the old days, the lack of robustness that you had in that were not compensated by anyone. But now the connection with ADRC is so clear, whatever nonlinearities you excite in the maneuver can be cancelled by estimation of those nonlinearities, and then what you're regulating is really the linearized system to go, which is completely controllable, to go from one place to another in the state space. So when you linearize the system around that operating point, the dynamics becomes very nice, very simple. The horizontal acceleration is related to U2. The vertical acceleration is related to U1. You remember, U1 is the force to lift the airplane. U2 is sort of a torque that interacts in order to let it change the horizontal position. When you apply some torque, the forces will push the airplane to go to a new horizontal position. And of course, because of the interaction, when you do that, the force has to be modified, the lifting force has to be modified in order to have a nice transition without going down. But this is the linearized system. It's a sixth order linear system. You have two control inputs, U2 and U1. Evidently, in the linearization, this system by itself is already a nice, simple system. U1 can control Z sub delta apparently with no problem. But then U2 is left with the task of controlling two things which are rather different. And normally you cannot do that. So the nice thing here would be to have two outputs, each one of them controlled by the control U1 and U2 respectively, and at the same time to be able to cancel this interference or this interaction, and be able to control, as a bonus, being able to control X, Z, and theta. This is the problem. This is why flatness becomes so handy, because now you examine the properties of this linearized system, you establish the controllability matrix of the system, which is 6 orders, so this is a 6 by 6 matrix. You choose B1, then AB1, and that gives you a second, two independent columns, B2 and AB2, all the way to A3, B2, will give you another set of independent columns. And this is done by trial. You put B1 and B2, and then you start filling the controllability matrix, and you will find that with this choice, you have a 6 by 6 matrix, which is full rank. So you take the controllability indices, or the Kronecker indices, as 2 for B1 or U1, and 4 for B2 or U2. So you have 2 and 4, 2 and 4 is 6, 6 is the order of the system, this is okay. There should be 2 flat outputs. Now you take the inverse of the controllability matrix and you multiply it by the Kronecker matrix that contains zeros and ones. In the first column you will have 0, 1, and the rest will be zeros. And then 2 and 4 is 6, so you will have 5 zeros, a 1, and that will be the Kronecker matrix. That multiplied by the inverse of the controllability matrix times the state gives you the flat output. And it turns out that the flat outputs are the vertical component of the motion and a combination of the horizontal displacement and the angle. That's very nice, because with this flat output I will control the height, the vertical coordinate of the airplane, and with this other flat output I am controlling a combination of X and theta. It turns out that these are the coordinates of the center of oscillation, and in the nonlinear system that will entitle sines and cosines reflected on the airplane in an axis that is off the plane. There is no eraser. Okay. Yeah, that's a nice physical output. If you have the plane like this, the center of gravity is located at this point, X and Z, and if you put a perpendicular axis to the plane, here is the plane, there is a point here that represents the center of oscillation, and guided by that in the nonlinear system you can discover that that is the flat output, and the linearization of that flat output is just that. So it's a little bit different, because the linearization you lose a lot of information, but that's the set of flat outputs.
How did you go from the inverse of controllability matrix to the flat output?
Multiplied by the Kronecker matrix. The Kronecker matrix is this matrix of zeros and one. You have two outputs, so it will have two rows. The controllability indices are gamma 1 equals 2, gamma 2 equals 4, right? Yeah. So you put 0, 1, second position, and 0. It's a 6 matrix. And then the second row, there's only two flat outputs. This will give you the first flat output. The second flat output has a controllability index, the Kronecker index is 4, so 2 and 4 is 6. You have to add the indices, so 3, 4, 5, 6. This matrix multiplied by the inverse of the controllability matrix times the state will give you the two flat outputs, y1, y2. Okay, this is the controllability matrix that you have chosen with these particular Kronecker indices. And that's how.
In the method, you use the observability.
Yeah, this matrix comes out of the product of the observability and the controllability matrix, which gives you a lot of information about the input to state relation, state to output relation. And the product of those two matrices, they can be thought of as taking part in a transformation. The observability matrix, you have the freedom to choose it orthogonal to every column of the controllability matrix except with the last one in the Kronecker block.
You didn't have to do that here.
Well, but because the formula was already worked out.
Right.
So the formula is the same for all systems.
So you didn't go from state to output. You go from state to flat output directly. Here, the output would not be defined, right?
No, I mean flat outputs.
Yeah, you go to flat, but in the original problem,
Yeah,
was not defined.
yeah. Remember, the flatness is a property of input to state.
Right. Right. So
The output doesn't
you
have.
go from the state to the flat output directly, without
Yeah.
going through the observability.
This formula, I think we call it the Kronecker matrix. It's a Kronecker that indicates you the position of the indices gamma 1 and gamma 1 plus gamma 2 in a matrix with as many rows as flat outputs there must be. And the relation with the Kalman controllability, with the chosen controllability matrix, because you have a choice, is C inverse X.
So basically you chose the second row of the controllability, inverse controllability, and the last row. That's essentially what it does.
No.
Well, if you look at it,
No, this is
the row one is last row.
this is the last row is very different.
Last row 1 minus. See, that's how you get your
Oh yeah, but no, but this is the flat. Yeah, because
right?
because the indices in this case is 1 and 2 and 4.
Yeah, 2 and 4.
So 2 and 4. But
Right.
but it's not like that. Be careful. It has to be done through this matrix.
Of course, yeah. But
And here you have the freedom to put any alpha and beta.
right,
But in order for simplicity, we just put ones and one.
formally, but somehow you're able to do that by inspection, right?
Yeah, from the inverse of the controllability matrix, but remember that entitles a choice, and that choice is defining what this is. It froze.
Click on it.
Yeah, thank you. Yeah.
Further.
Yeah. Okay. Thank you. So so in that case, this is the inverse of the controllability matrix that you have chosen from here. You chose this arrangement of column vectors of the Kalman matrix, taking only 2 dimensions for B1 and 4 dimensions for B2.
Yeah.
As subspaces that you can influence directly. So you have that. But the issue would be to obtain the flat output from here by inspection. Of course, this is already telling you this has to be a flat output because it's an independent subsystem that is not related to the rest. And therefore, how are you going to compute C sub delta in terms of X and theta? There's no way. Because C doesn't appear in any of these 2 equations, so C has to be a flat output, which is already controlled by U2, U1. So the other flat output you have to figure out from the two other equations when you want to do it by inspection. But there is a formula, systematic formula for obtaining that. So so now that you have the flat outputs, you just invert this relation to find find a number of derivatives of f1 and f2 to find the differential parametrization, and that's basically differentiate the f1. You know that if you differentiate it twice, you will get the first control. But if you differentiate f2, you have to differentiate it 4 times to get the second control. So when you do that, and now you have, all the relations of the derivatives of f to the state, you can invert that relation and obtain all the states and the control inputs in terms of the flat output and its time derivatives. So it comes out to be something like this. X is parameterized by f2, z is parameterized by f1, which is sort of independent, and theta is just minus f2 double dot. And u1 is f1 double dot, and u2 is minus f2 to the fourth. The gain is very important here. So the gain here is negative. Now this system is a very nice system. It has all this structure. It's a controllable linear system in which you have identified 2 subsystems of dimension 2 and 4, represented by f1 and f2 respectively, that completely parameterize all the 3 state variables, and of course the velocities would entitle f2 dot, f2 triple dots, theta dot would entitle f1 dot, and theta dot will entitle minus f3 dot. And this system is non-minimum phase. How do you know it's non-minimum phase? Well, when you try to drive x to a constant value or to 0, because this is an incremental value, you have an unstable differential equation here. So that's a non-minimum phase output if you were trying to regulate x by itself. And C wouldn't have any dynamics, because C is already a flat output. But you can find many things from this parameterization. You see the relations of the angle with those gains are very important, because they tell you a change of sign that needs to be done, and it's not intuitive.
You say the non-minimum phase output as well?
Who?
Say the angle.
Well, if you put theta equals 0, and you start from very small initial conditions, f2 will be unstable. So the combination is that you have instability built up in the 0 dynamics, not only of x but also of theta, not in C.
So both theta and x are non-minimum phase output.
Non-minimum phase.
Somehow the linear combination of it
is minimum phase.
minimum phase.
Yeah, that's the point. That's the point. The right linear combination that you need to overcome the internal stability. The other possibility is just to see that f2, when x1 is 0, you get an unstable differential equation. So the control objective is to bring the original nonlinear system to a constant equilibrium, and that can be achieved by driving f1 and f2 to 0 independently, and that can be done by means of many pole placement and many other things, because you have the dynamics for f1 and f2 as related to the inputs. So f1 is related to input u1, f2 is related to input u2. Yeah. I won't give you the controller, because just for illustration purposes, I use here a sliding mode controller, but that doesn't make much sense. But it does produce some nice responses and so on. For going far away from the equilibrium point to a location which is, not in the vicinity of the system, and clearly the non-minimum phase character you can see there somehow. But this is sliding mode control, which doesn't have anything to do with. And now, of course, you can solve tracking problems with this parameterization and this input to flat output relationship. And you want f1 to follow a certain trajectory, you want f2 to follow another trajectory. Of course, that's a trajectory that has to be prescribed by due consideration of the relation of the flat output with the states, and also, watching for limitations in the controls. So, you know, you can do trajectory tracking by feeding the proportional controller which has proportional derivative precompensation or feed-forward term in the traditional manner. But this is just linear state feedback using the flat outputs and the derivatives of the flat output, which are the phase variables associated to each flat output. Here you have a second order system, so you have proportional derivative controller. If you can measure F1 dot, which is related to the states. If you measure the states, you measure the flat output and its time derivatives. They are all related to the states. So if you measure all the states, you can implement this controller. And U2 is controlling a fourth order system. You have, you know, the error, the tracking error, the derivative of the tracking error, the second derivative, the third derivative, and the precompensation or the feed-forward term, feeding the feedback law for U2 and U1. And the nice thing is that you can control the nonlinear system with this control law. And in fact, this is what we did here. We used the nonlinear system equations to apply that linear-oriented control and moving the state from one position. These are all normalized values of the variables, but they're significantly far away from the equilibrium position. So you have reasonable controls, you have the response of the horizontal coordinate, the vertical coordinate, the angular position and the control.
How did you obtain F star from X star and Z star?
Oh, because I wanted to do a maneuver to go from one location to another. So you know the initial, because of the parametrization, here you have the relation that allows you to do that. Let me show you. Let me show you, because that's an important point. From this parametrization, you say, okay, I want to elevate the airplane from a certain initial value to a final value. So that is immediately tells you what is the initial value of F1 and what is the final value of F1. Now you prescribe a trajectory that takes you smoothly from the initial value to the final value, and that will prescribe you F1. And yeah, and F2, if you say I want to drive horizontally the plane, I want to move it far away from the equilibrium point. So I want to start in equilibrium, I want to end up in equilibrium. In equilibrium, this thing will be 0, and therefore this will give you the initial value of F2 and the final value of F2. And if those values are constant, the second derivative is 0. So in this map, there is nothing hidden, there is nothing difficult unless you have a control objective which is non-traditional. And that's what happens in the plant model.
What about intermediate value? So you have initial value, you have a final value for X, but also you have the desired trajectory.
Yeah.
So how do you translate the desired trajectory in this case to the trajectory of F star?
The trajectory of the nonlinear system?
No, you construct a F star, which is trajectory, trajectory for F, right?
For the components of F1 and F2.
Yeah, for, in this case, F2 in particular.
Yeah.
You have to move X in a particular manner.
Yeah.
In this case, how did you do that?
I only need the initial and final values, which correspond to the initial and final position for F2. Right. This influence is in between, the acceleration that you will pick up. Right. But you're sure. One of the important things, and this is a very important question, and let me bring you to the concept of controllability. What is a controllable system? There's an important definition given by Williams many years ago. A controllable system is a system that can connect the past with the future smoothly in finite time. That's a controllable system. And he showed this by means of the behavioral approach, that this definition that he gave like that corresponds rigorously to the possibilities of tracking trajectories. That means controllability in the case of linear time invariant systems. Controllability means the possibilities of joining the past with the future through smooth trajectories, smooth connections in finite time. And that was also established by Michel Fliess in the module theoretic approach to linear systems. Controllability there has an algebraic interpretation in terms of the module of the system. When you generate all possible equations that can arise from a set of equations, you create a structure into all those infinite possibilities of equations through a certain ring, the ring of differential polynomials. That is at the heart of linear systems. And what does controllability mean in terms of modules? In terms of modulus, it means the freeness of the module. A free module is a torsion-free module. A torsion module is a module which is a vector space in which the variables satisfy differential equations. If the variables don't satisfy differential equation, then you can control them. Those portions of the uncontrollable system are because somebody is satisfying a differential equation that cannot be controlled. That is the notion of lack of controllability. Something is not controllable because that variable representing that particular phenomenon satisfies a differential equation by itself and cannot be influenced by anybody. That's lack of controllability. But in module theory, as well as in the behavioral approach, the possibilities of joining trajectories from the past with trajectories on the future by means of a smooth, that means, you know, the connection is not discontinuous, the connection is very smooth, with smooth trajectories in finite time. And that's what allows you to do that here, because it corresponds exactly to the same notion. So this is why trajectory tracking works so well.
That in that equation, if you go back to this equation, how do you determine F1 star? That's a function of t. That's not just a finite.
It's an interpolation polynomial.
Okay.
This is what I have spoken on several occasions here. When you have a rest-to-rest maneuver, you just put a Bézier polynomial.
Okay.
That's a polynomial that connects 2 points in a smooth manner, in the sense that it satisfies the extreme conditions, but the number of derivatives of this polynomial in the beginning, at the initial point, and at the final point are all zero. So you have a very smooth connection with constant trajectories, because not only the first order time derivative, but all the derivatives that you need will be limited by the order of the polynomial you put, will be zero, but it will go smoothly from one point to another. You can also use trigonometric functions to planify trajectories. That's sort of a nonlinear solution, but polynomials are very nice. You can have a table of those polynomials, have them in your computer, and use them every time you need them to planify a trajectory from one initial point to a final point.
So back to your so that's how you define F star and Z star.
Yeah.
You define F1 star, and then you come back. You compute the X star and Z star based on F1 star, right?
Yeah, because of the relation you have.
Okay.
Yeah. Yeah, that parameterization allows you to do that. And here's a controller for the quadruple tank system in the linearized version. It's also a multivariable system, as we saw in the first lecture.
Professor, do you want to take a break? A few minutes break?
Okay. Okay.
It's almost 2 hours, so you want to take
No problem.
have some tea?
Yeah, please.
It's nice idea.
Yeah, it's very useful in a large class of nonlinear systems. Proceed by first linearizing and then using the flatness to prescribed trajectories, analyze, and then solve the problem. This is for the quadruple tank system, in which you had 4 tanks with the upper tanks fit in different tanks, and 2 control inputs. So the linearization of that system is a simplified version is just that. And the outputs you want to control is the heights of the 2 lower tanks, and the system is linearizable around an equilibrium point, and you have this description for the linearized system. So here you have to choose a Kalman controllability matrix, because it's going to be having 2 columns and the system being 4 by 4. You have 8 columns and 4 rows in the controllability matrix, so you have a lot of freedom to choose a rank 4 matrix, sub-matrix that somehow involves the 2 input channels and the rest of the dynamics. So we choose the controllability matrix as this one, as B1, AB1, and B2, AB2. So the Kronecker indices are going to be 2 and 2. Gamma 1 will be 2, gamma 2 will be 2. And that gives you a 4 by 4 matrix, which is full rank. And all these distribution parameters between the upper and the lower columns of tanks are everywhere in the controllability matrix. So these distribution parameters, which are constant, tell you a lot about the structure of the system and how to control it. So you take the inverse of that controllability matrix, you find this Kronecker matrix of zeros and ones, and you get the flat outputs. The flat outputs are not intuitive. They are a linear combination of H2 and H3 for the first one, and a linear combination of H1 and H4 for the second one. So H1 and H2 are the lower tanks, and H3 and H4 represent the incremental height in the upper tanks. And so you have a lot of interaction, and the flat outputs reflect the important interaction, and you can now proceed to find the differential parameterization in terms of F1 and its first order time derivative, F2 and its first order time derivatives related to the 4th state of the system. Now you can solve for the 4 states in terms of the flat outputs, F1 and F2. And you get this differential parameterization. Is a very nice differential parameterization in which you have this dependence on the 2 flat outputs. You see that there is a lot of interaction. The second flat output is present in the first tank, is also present in the second tank. In the third tank, there is only 1 flat output influence in that, and the 4th tank, there's only 1 flat output influence in that. But in the lower ones, those are the ones you want to control, there is a lot of interaction. Fortunately, you can analyze, from this parameterization, you can analyze, the relations. What happens if I make this incremental height equals to 0, if that incremental height is equal to 0, what is the underlying governing equation? And it's all related to that in that parameterization. So you can obtain also the input-output parameterization, and it reveals that you have, at the bottom of everything, you have two second-order systems, which are somehow, in a way, it's not that they're entirely decoupled, because F1 contains a combination of 2 states, and F2 also contains a combination of 2 states. But in terms of the flat outputs, they're pretty independent, in the sense that if you control F1, I mean, you only need information from F1 to cancel these contributions and to control F1 through U1, and also the same with U2. and gamma 1 and gamma 2 are ascribed to the two different options in a clear way. So the control objective is to take this incremental height to 0. H sub delta is a vector. So the input differential parameterizations will immediately suggest you how to control the system, because this happens to be a stable system and this happens to be a stable system. So in fact, this is already revealing to you that if you don't do anything, this thing will regulate by itself. This is one of the characteristics of the tank systems, or many arrangements of tank systems. You don't do anything, sooner or later the thing will stabilize to an equilibrium. It's probably not the desired equilibrium, but it will stabilize to an equilibrium. So they are called self-stabilizing systems, and Flatness reveals that feature directly there, because it's unquestionable that if U1 and U2 are set to 0, the F1 and F2 converge to 0. And therefore, if F1 and F2 converge to 0, from the definition of F1 and F2, if this converges to 0, so H2 converges to something proportional to H3, and H1 converges to something proportional to H4. So many properties of the system can be obtained from this, the parameterization and the input-output and the input to flat output parameterization. And you can control the system immediately by saying, here I have a second order system to be controlled, and here the same, so I will put a proportional derivative controller. This is a proportional part derivative controller. Because F1 dot and F1, they are related to the states, and if you measure the 4 states, F1 dot and F2 dot don't need to be synthesized as time derivatives in your algorithm. They are just new combinations of the states. And if you measure the states, you're done. So in terms of the actual states, this is the control law for U1 and U2. It's a linear control law. And it's very nice because it buys you a lot of things. Of course, when you do have perturbations that the non-minimum phase underlying this system and many other issues related to a nonlinear system, which is rather complex, are not obvious. And I have a presentation that I made with a joint work with Conchi Wang. Okay, I don't know how to pronounce his name. In which we solved the problem for the nonlinear case, which is kind of complicated with disturbances everywhere. And but in this case, the clean case, linearization already gives you a solution of the problem in terms of measuring the states. If you cannot measure them, then you'll have to estimate some of them. And so the closed loop system for the flat outputs is immediately forced to be stable with now with the rate of convergence that you can prescribe in terms of the natural frequency and the damping. So you can simulate that you can go relatively far away to new heights. Bring the first height from 0.5 from minus 0.5 to 0, from 0.5 to 0 for the second, the third from 0.5 to 0, and so on. And the controls will still be reasonable. And so that, I think that's the end of it. Okay. Any questions? I can show you another examples like the crane example and so on, because it's basically the same. It's linear systems, mechanical linear systems. Okay. And
you need to leave for lunch.
No, it's 12:30. Okay. Now it's 12:10.
Let's see a crane. With Dr. Jiang.
And that's a typical multivariable system Of course, I can give you many others if you want to see that. Flexible pendulum crane, flexible crane pendulum. I have another ship control. Let's see if it's this one. Yeah, in this case, let me show you. You have a multivariable system. Can you see this? This is a simple system. It's not. Oh, but I think this is not right. This is another crane, a different crane with a pendulum. It can be controlled by flatness and so on, but what I had in mind was different. Okay. Flexible pendulum crane.
它这个用在就这种机械东西里，它好像用了很多。
Okay.
在 processes 里边，在biomechanics
现在外国
机体人里边肯定有。
机器人里面肯定有，但是外国里面现在的热点就是如何帮助人，这个能力。
Oh, this. I'm sorry. I keep bringing examples that I cannot present yet because they're not finished. But that's also an example of a multivariable system in which you have two controls fundamentally, this control and this control. You have the torque and the motion of the car. And here you have some flexibility between these two arms. And you have a load which is not controlled. So it's an under-actuated system. That's one of the nice features of flatness is that under-actuated systems which have a controllable linearization are very nice examples because you can control the nonlinear system controlling the linearized system by means of flatness and good trajectory planning. It doesn't represent an obstacle, the fact that the system is nonlinear, as long as it has a controllable linearization. And this system happens to have a controllable linearization. And, you know, it's a second, fourth, I think 6/8 order system. But still, you can manage to find the flat outputs and so on. The flat output is related to the center of oscillation, so it's a linear combination of some of the states that comprise the two links and the pendulum, and therefore it's flat. Let me show you some other thing which has simulations and everything.
I think the critical step is you go from problem to the flatness, to flat output. Once you found flat output, everything else become much easier.
Yeah.
The critical step is from the
yeah, because everything is sort of linear. In the back of your mind, all your problem becomes a linear problem.
Right. Yeah.
And
so that's a critical step. Can you find a difficult problem
no,
where the flat output may be easy? I think human already found it. Right? Yeah. 叫什么爆散、炸散、点散、不一般的点散。对不对？ 把一个非对角相位的问题用这个 flat out 给绕过去，很巧妙，巧妙。你学习，我们起点都是一样的，它也能给用上，它也能给用上。怎么样？
学以致用。
这个，因为这个东西完全是你怎么看问题，不是跟你学了多少什么那个微积分啊，不是，当然需要有一定的世界背景。还有那个鲁邦性的这个问题，他来了以后，我跟他讲，我说这个AD2 跟鲁邦控制应该有个很好的结果，就是这个 PD 控制器这块儿，把 ESO 把这东西给清掉以后，剩下的还有估计动静，这块不动静跟鲁邦控制里边那个问题就很相似了。但是呢，那个鲁邦控制的缺点就把所有不动性全用一种控制器来那个，所以它非常保守。这个系统好像挣扎了几个星期了，对不对
Sorry.
后来做出来也很漂亮，做得很漂亮。就是在那个低频增益能够提高很多，带宽能够提高很多，就比那鲁邦控制用那个工具箱做出来的，是这样的。所以就这么一个想法，但是我觉得这个可以有个借鉴。这块就需要这个灵感，他给你东西，他不可能都一样，他要告诉你怎么做出来，那你就尴尬了。就你怎么把这个新的思想能够结合到问题东西，就这块，搞工程就是这个含金量特别大。所以我觉得从他的例子可以看到那个一些这个路子。
其实有个结果，
比较他有比较正在写文章，你以前有是吧？
是哪一年？就是这个人底下有关，就这样。但是鲁邦那里还是用这个方法，鲁邦这边不是一个情况。
就鲁邦控，李老师说鲁邦控里边有好多东西，薄膜也是一个。我们说的鲁邦控就是那个 traditional 鲁邦 control， 那个 H 无穷那个MIMO synthesis 那个东西。
Yeah. Typical example is the three. That's a typical, but that's monovariable, but it's non-flat, and you can linearize the system, find the flat output, and then planify your trajectories on the basis of the flat output, and control it from an initial position to final position in a nice manner. It's a non-minimum phase system, highly unstable, but at least in simulations you can get a good performance. And you can see force being applied and so on. But I have some multivariable systems that I would like to show you. And this is the Acrobot. The Acrobot this is the only actuated element. And what you want to do is to do a trajectory, a rest-to-rest trajectory without this pendulum, which is free, doesn't fall down. And this is also something that Flatness allows you to do very nicely, because you do the maneuver, without losing the equilibrium, and everything based on a linearized model. Of course, the PVTOL system. What is a PVTOL? Okay, this is a complicated example in which you have you know, a spring between these two, and you have a pendulum that is free to rotate. So in that particular case, you have, you know, you want to go away and come back. All sorts of maneuvers. You can really, flatness gives you so much freedom that you can actually, you know, be very creative about the kinds of maneuvers that, let's see. Okay, this is the other one, the one with the flexibility, and which you also want to, here you have two controls. One of the controls is the motion of the car, and the other control is the torque applied to the first link. The second link is unactuated. And you want to bring it from an initial position and initial equilibrium to a final position and final equilibrium. And because it's multivariable, the linearization happens to be flat, and so you can do the maneuver without oscillations. At least here in simulations. In real life it might be a completely different story. But that's something that you can do with flatness. Pardon? Yeah, I think so. Yeah, I was looking for the paper. I couldn't find it. But it must be there. I just tried to find it. Yeah, the pivotal example is also a nice example. That's the pivotal example in which you have a rest-to-rest maneuver, and as you can see, far away from the equilibrium point, by doing exactly what we did in the presentation, you have a prescribed trajectory for the flat output, which is the center of oscillation, and you can go from an initial point to a final point, just tracking a smooth trajectory for the two flat outputs, and you will have a nice response. But the system is non-minimum phase, as we saw, and still multivariable and non-minimum phase, and non-linear. We use the nonlinear model to do the simulations, and those two little things represent the forces applied to the plane, and the stabilization around the point by tracking the trajectory.
This is very helpful.
Yeah.
Very helpful to see the effect.
Yeah. And here's one of the ships that.
Oh, the ship?
This is a ship, and it is commanded to follow a rather complicated trajectory. And here the flat output is very close to the position coordinates, and you see that they're following like if there were two tracks, but it's just the flat output following the trajectory that needs to be followed in order for the center of gravity of the ship to follow the other one. So, and we put some very noisy disturbances. At that moment, we didn't know anything about ADRC, but you still managed to have some kind of robust performance, and these are the trajectories in the XY plane. And just by linear feedback plus some integral control.
Do you remember where when this was published?
No, it was never published.
Never published?
No. It was not published. Yeah, that's the way it is. Life as it is. We never published that. We didn't even try. We didn't try to publish it. Things like that do happen. We have, you can also play around with heat equations, which is an approximation to a partial differential equation in which you have applied heat to this phase, and you want to transmit the heat from that side to this side, and you have the level of heating, and you see how the different portions of the slab are being heated until you get to the final equilibrium for the desired value of the heat here. You want to control the amount of heat here, or the temperature here. And so So that's a very nice flat system also.
This is generated by.
Yeah, yeah.
Do you know how to do this? Yeah.
Of course he does. Of course he does. Of course he does.
They're very nice. This is much better. Yeah.
And yeah, and this is the one subject to perturbations and so on, but it's like the 3 disk but horizontally without the gravity now. Yeah, so you're applying torque, and you want to regulate the
Three-day torsion. We can do that, right?
the position of